Hello everyone, I'm Andrew. I'm here today with Leon, and we're here to discuss Rust code in Qt applications and the challenges and solutions around them, and particularly why this is difficult with Qt applications rather than just plain C++ applications and bridging to Rust. So first, let's consider a typical Qt application. This should all be very familiar to all of you. So this is just a simple to-do application. It's written in QML, but it could be widgets as well. You can add a task, and then you can complete it. If we consider the code for this in QML, that would be a list view, a model, some kind of delegate that is reading from the model and potentially updating the state of the model. And this is very typical in your Qt application. You normally have some kind of view and some kind of model. And again, this would be similar for Qt widgets. So if we consider this in an abstract sense, you have a presentation there on the top. This is made up of views, components, and is either QML or widgets, or maybe a mix. And then you have some form of business logic data that's basically state that is aggregated and then presented to Qt through abstraction models. But where can Rust be useful to us in this? Let's consider first, where is Rust useful and what's its advantages? So Rust is a memory-safe language by default. It has bare metal performance like C and C++. There's no runtime or garbage collector. It allows for fearless concurrency through safe and easy multi-threading, which is particularly challenging in C and C++. And it's using modern systems for easy dependency management, and has a rich library ecosystem that you can easily use through Cargo. This has all led to Rust being the most admired programming language since 2016 in the Stack Overflow Developers Survey. So let's consider our abstract diagram again. Where do we think Rust would be useful here? Well, it's the business logic and data layers that Rust really shines. It can accumulate the data, whether it's unsafe or safe, and it can quickly accumulate this safely across multiple threads, and then we would want to present this up to Qt. And Qt is easy to use, and particularly in QML's case, is declarative and fast and iterative. So we'd still like to use Qt for the front-end logic. So which code would be affected if we just wanted to use Rust for our backend? This would just be the model. And Qt already has abstraction layers between the view and the model for us, so we can utilize this going forward. So to summarize, we want to use Qt's existing abstractions, such as QObjects, QAbstractItem model, or maybe the even more advanced ones, such as QQuickPaintedItem or FrameBufferObject. We want to use Rust primarily in the backend. We don't want to use it for the front-end logic. This is due to widgets case where there's a lot of raw pointer API, and it wouldn't be ergonomic to use this in Rust. And in QML, it's already declarative, has property bindings, and is very easy to use. So Leon, how do we get there?
So the first question we should kind of ask ourselves is, well, can we just use existing C++ and Rust binding systems? Because Rust is often touted as sort of a language that can solve similar problems to C++. So people already have, of course, worked on this problem of how to integrate Rust into an existing C++ application. And indeed, there are many existing options to do this. However, they are really limited to standard C++ concepts, because that's what these approaches deal with. And we really need to remember that Qt goes beyond what just standard C++ can do, because for standard C++, we could maybe express some of Qt's very basic types for data exchange, like QString, for example, which is kind of like the one thing that made Qt famous in the start. And for that, we can absolutely use existing C++ bindings. But if we also consider that we need to go beyond just the API of Qt, which, well, of course, is made of some types and libraries like widgets, Qt also has its meta-object compiler and meta-object system. And this is something that just is not standard C++, right? It's implemented by Qt's meta-object compiler, so it's a layer on top of just standard C++. And this is what really enables QObjects, QGadgets, signals, slots, properties, and just in general exporting data to QML and registering new types for QML. And that is really the thing that is particularly difficult to do with Qt that you don't have in a normal C++ library if you want to integrate it with Rust. And this is really kind of the big important thing to kind of crack if you want to do Qt programming with Rust. And this is something just normal C++ bindings will not give you. Also, ideally, we want our code to work in our existing Qt and C++ applications. We don't want to throw everything away and rewrite everything from scratch. So that, of course, in many cases means we want to integrate it in a CMake. And also, Qt goes beyond just normal CMake libraries with, for example, QML modules, which are a whole sort of CMake library and interface on top of just normal CMake targets. And that, for example, gives us automatic type registration in Qt 6. And those are things we, again, don't want to lose. We don't want to go back to having to specify all of our types again, like we have to do in Qt 5 when we're using Rust. So just as a reminder, right, the build in general with C++ still looks like this. You have your annotations on your class, like QObject, QInvocable, QSignals. And these things look like macros, but what really happens is this is input for the meta-object compiler. The meta-object compiler will parse your file, and it will look out for these macros, and it will generate additional code that, for example, implement your signals or does type registration and all of these things. So if we want to do the same in Rust, we sort of have two important challenges to deal with. Well, first of all, we don't have a QObject macro. So what's the API even going to look like? We don't really have classes in Rust either. We have these structs, and we have implementations that are actually outside of the structs. They are still member functions, but they're just implemented separately. So maybe we need some kind of different API here. How do we even express these macros? But then, of course, also we need to be able to run mock. We need something that understands these annotations and can give us an actual generated code like mock does for us. So how do we do this? Well, let's first explore the options that currently exist. Again, remember, there's three big things to keep in mind. We have Qt, which has a huge API surface. We have mock that we somehow need to emulate for Rust. And we also want to integrate all of this with CMake. So one of the very first approaches to this was just focusing on the API surface. And that was an approach called Ritual, which was an automatic binding generator. So that could parse your C++ headers and generated you a ton of Rust bindings for them. But those were also essentially unsafe to use from Rust. And unsafe Rust code just negates a lot of the benefits of using safe Rust to begin with. It's almost like writing C++ code again. And on top of that, there was Rust Qt, which are the Qt bindings generated with Ritual. So those do give you a huge part of the Qt's API surface that you can interact with from Rust. But that's the one key point. You can interact with it from Rust. You can't actually export data from Rust to Qt. You don't have mock for Rust. Also, this crate has been largely unmaintained for the last 4 years, so I would not really recommend using it right now. Then people at some point realized we need mock for Rust. What do we do? And KDE came up with the Rust Qt binding generator. And that one didn't actually yet quite solve this question of how do we do this in Rust, because it actually moved all of this annotation data, so properties, signals, and slots, into a JSON description that was outside of actually the Rust code. So that would then run through a version akin to mock and generate C++ and Rust code for the actual bindings. And all of this was really based on a standard sort of extern C FFI. So like going back down to the very most basic building blocks of interaction between Rust and C++. Right. So that sort of solved the mock problem, but didn't really solve the API problem. So now we have two separate parts. Well, there's also QMetaObject.rs, which is yet another approach to the second question of how do we build mock for Rust. And what they really started using is, well, they started putting the API inside of Rust. They used Rust-derived macros, and because that was at the time the only kind of macro that you could do procedurally, they had to use like special member types to put everything into the struct type, and could then from there basically implement their own mock for Rust. That was at least written in the Rust syntax, even though it used some very special member types that weren't really members, but sort of functions that were implemented outside, that sort of thing. But at least you had something in Rust. However, this is actually only available with Cargo as a build system at the moment, and really hard to integrate with Cargo. It also doesn't really deal with the whole API surface problem, because it also uses a crate called CPP, which basically lets you write C++ code just inline in your Rust code. And of course, that C++ code is going to be just as unsafe as it were if had you written it in a .cpp file. So again, we're negating a lot of the benefits from safe Rust code. And a few years ago, we at KDAB sort of took a look at a new approach that came up when it comes to C++ and Rust interop, which is a crate called CXX. And what CXX really does, it gives us safe, but also bidirectional access between Rust and C++. So we thought that might be a really good basis for the next approach on how to do Qt and Rust bindings. And that can already give us a lot of the sort of interop situation on the API side, and also gives us safe Rust code. Now, we can call C++ code safely from Rust, and that's a huge advancement. And also, CXX itself uses a domain-specific language that is also using Rust syntax, more or less. It basically gives you external C++ in Rust syntax. And it also is nicely compatible with Cargo and with CMake. And so we thought this would be a good thing to build upon, and which is how we implemented CXX-Qt, which is more or less mock, but on top of CXX. And Andrew will give you first a bit of a whirlwind tour of how CXX works, so you know how we dealt with the API bindings, and then we'll also talk about how we built mock on top of this.
Leon. So yes, let's look at CXX as a modern way of bridging between Rust and C++. So this is an abstract diagram of how CXX works. It starts at the top with a CXX bridge macro. This is a description of the boundary or the bridge. And if we go down the left-hand side first, you have macro expansion that occurs. And this ends up generating your Rust binding side. And these are safe, straightforward Rust APIs to use. And they are very idiomatic to Rust. On the other side, we have code generation that occurs. And it ends up generating C++ code. And again, this generates normal-looking C++ code that is straightforward to use. In between, it actually uses a hidden C ABI to do this, and it creates static assertions and things to check at compile time that the types are correct on either side. So the main invention of CXX is that it adds more extern block types. So Rust already has an extern C block, but this is only useful for C. So it allows you, the first one is to declare an extern CPP block, and this allows you to define C++ types and signatures to be made available to Rust. And as this is our first bridge here, you can see we've got a CXX bridge macro. This is on a module, and that allows CXX to understand where you're defining the definitions. So then inside this module, you then put your extern blocks. And you can see in this extern block here, we've described a QPainter very basically. So there's a type, QPainter, and we're telling CXX there's a drawRect method on that type. And this will be exposed through the macro expansion in Rust, and it will appear like a normal struct with a method for us. And of course, CXX has the opposite direction as well. So you have an external Rust block. And this is for declaring Rust types and signatures to be made available to C++. Again, we have the bridge, and we have a type and a method. And this would expose that struct through to C++, and it would appear like a normal class in C++. So you can already see how you could use CXX to define normal Qt types, such as QString. And we've already done this with CXX-Qt lib, a crate that we have, which is a collection of the common types you would need, most fundamental types you'd need to bridge between. These focus on high quality written bindings and stability guarantees. And then we have a second crate called CXX-Qt lib extras for any community contributed ones that may not necessarily be stable. But we have a problem still. CXX by itself, as Leon mentioned earlier, doesn't know what mock is. It only knows standard C++. So we've created CXX-Qt, which is a superset of CXX, and effectively provides you mock for CXX. So this allows you to declare signals, slots, properties, etc. And we have a whole set of libraries to help you build your API and bindings and create the whole Qt application. So let's have a look how the code generation would work. So similar to the CXX bridge, instead we have a CXX-Qt bridge. This again is on a module. And then we have, as you may see, instead of an extern Rust block, we have an extern Rust Qt block. And this allows us to define a type in Rust that we want to expose to Qt instead. We then tag this with QObject. Yep. And this allows us to express that we want a QObject. This then, through code generation, generates a normal looking C++ header, which then can be passed to mock. And then mock can do any type registration, any extra code generation it needs to. And then all of these are combined together into the final binary. You may also want to note here that for the ownership side, the Rust inner struct is actually owned by the C++ class. So let's compare what you would write for C++ and Rust for some basic CXX-Qt examples. So if I want to create a QML element that is a QObject in C++, a very simple one would look something like this. We have a class inheriting from a QObject, we put our macros in, and we might have some private state. On the Rust side, it looks very similar. We have our type, we have the attributes, which match the macros, and we have some private state. You can see again here how our private state here ends up being owned by the generated C++ class. If we move on to a property, in C++, you normally have some kind of field storing the property, and then you have your macro that defines the type, the property, whether it's read, write, notify, etc. And on the Rust side, again, very similar. You have your property, where the field's stored, and you have your attribute. We actually have a shorthand here, so you don't need to specify read, write, notify, but you can, of course, add them in and override as usual. Invocables are again similar, but there's a subtle difference here. So you have the QInvocable defined in your header in C++, and then you have the source. And in Rust here, we see our first example where you have the definition in the bridge, which is Q-invocable, but the implementation is actually outside of the bridge, and the implementation is on a type coming from the bridge. You may think this is similar to having a header file and a source file in C++. And again, for signals, very similar. So to summarize for CXX-Qt, you have a bridge macro. The actual macro itself ends up acting in a very similar way to the C++ header. You then have an external Rust Qt block to declare any Qt types in Rust through to C++. And we also have an external C++ Qt block to use external C++ Qt types in Rust, such as being able to teach it about signals. So Leon, what does this look like in a more complete example?
Yeah, so now let's actually go just very quickly through how we would migrate something like a simple to-do example to the Rust side using CXX-Qt. So let's first remind ourselves of what is really kind of the minimum we need to do in order to get a model through to QML. We really need to inherit from QAbstractList model. Then we need to define a role names function. Of course, this is not really needed for widgets, but we are doing QML here, so we want the role names. We need the row count function, the data function, and in our case, we're also adding two invocables, one to set an item as checked, so a to-do is being checked, and to add new to-dos to the list. In our case, we'll just be using begin and end reset model because we don't really want to deal with the data insertion here. It's more about how we do the Rust integration, but of course, in your actual application, you'd want to probably do this a bit more cleanly. And so let's go ahead and first of all declare a Q object that's also a QML element. In our case, we're just going to call this the to-do list. And again, we have our actual private state in a struct outside of our actual CXX-Qt bridge. And the advantage of this is this means you can actually have whatever Rust state you like. No matter how complicated, you can have it in your Q object type. Doesn't matter, you're not limited to like only types that are compatible with C++. You can do whatever you want inside of your Q object. And in our case, we're just adding a vec, which is a vector basically, in Rust speak, with a tuple of booleans, so whether a to-do is checked, and a Q string, which tells us kind of what the task is for our to-do. And you'll notice here already, we can just immediately use Q string. That is because we've imported CXX-Qt lib, which already gives us bindings for these very basic types, and we have taken a lot of care to wrap them with very high quality so that they don't feel out of place on the Rust side. Then, of course, we need to also inherit from QAbstractList model. Now, there's a bit of a catch here. Rust doesn't really support inheritance. So what do? Well, with CXX-Qt, we simply add a new attribute that allows us to still specify what we should inherit from, and this is then passed along to our generated C++ class. And we can inherit from pretty much any class. Well, if we're declaring a Q object, it must, of course, be a Q object class. But we can just import the class from C++ using standard CXX syntax. In this case, we'll just use QAbstractList model. So you can do the same with table model or anything else you like. Then let's go over to the role names function. Usually, it's best practice to also declare a QEnum to go along with your role names. So we're doing the same here, and CXX-Qt totally supports adding QEnums. In this case, we're declaring the QEnum to be a member of the to-do list, because Qt's a bit interesting with scoping here when it comes to QML exporting. So we need to specify what the QEnum sort of lives on, either a namespace or another Q object. And then we need to tell CXX-Qt that we want to override the role names function. So pretty much like you would be doing in C++. Then, again, think of the bridge as your header. So outside of your header and in your actual source file, you're implementing the role names function. In this case, we're just creating a Q hash. Because this is a templated type, this is a bit less ergonomic than you might be hoping for. But we actually have some plans in how to improve this in the future. But we can still just insert types as normal and return it from the function. Then it's very similar actually for row count. It's just an override in the bridge, and then we implement it as taking the length, converting it to integer, and we're done. Then the data function is kind of where the meat of our model is, and that also looks probably very similar to how you'd write it in C++. You'd have to match over basically your role, which you can create from the integer that you get and convert it to your roles system, then index into your vector, then match, which is sort of a switch in Rust, and then you match over your roles and return the corresponding value. And you notice here that we are also very easily converting with .into Qvariant. Again, these types are coming from CXX-Qt lib. You don't have to do anything to get these. You can just download them freely, and you're done. That's pretty much it. And you can use Qvariant again with most of the types that you use to. Then we need to start adding our invocables. And in this case, well, we just declare an invocable and mark it as QInvocable. That's pretty much all there's to it on the sort of special Qt side of things. And then we need to actually implement the type. In this case, because we're mutating, and Rust is very careful about when you're mutating data from multiple places, how that is handled correctly. And therefore, there's a bit more sort of ceremony involved here. But once you're through that, it's in the end very simple. You get your mutable access from your member. In this case, Rust also forces us to check that there's actually a value at this index. So this is also error handled. And then we assign the value. And in this case, we've implemented it so that we just sort the model so that everything that we've checked is at the bottom. So we only see our tasks that we want to actually do next at the top. And that will also implement our model reset in our case. And then it's very similar. If we want to add it to do, we also just declare an invocable, and then we push something to our vector, and then again reset our model. So how do we do model reset? Well, this is actually something where, remember I said Rust doesn't have inheritance. So how does it deal with protected members? Well, it doesn't have that concept. So we also had to add that for CXX-Qt. And with CXX-Qt, you just easily declare something, so any function you basically want that is implemented in your base class, and tell CXX-Qt, by the way, I want to inherit this from C++. And CXX-Qt will do all of the basically checks that this function exists, that it's coming from the parent class, export it to Rust. And once you're done with that, you can just call the function and be done with it. So we just reset the model, then sort our vector by key and end the model reset. And that's it. Our to-do list works. And this is actually the exact same video that I showed you at the start. Because if we take a look at the code we had to change, it turns out this is the same code. We did not have to change any QML code because this was running Rust from the beginning. And no one even noticed. So that's the really cool part about it. We don't actually have to change anything from the QML side because we're using the exact same abstractions that we've had all this time. And we even allow you to make sure that your casing's the same, even though Rust uses a different style, all that sort of thing. And yeah, that's pretty much it. The only question remains is, how does this actually build? And Andrew will tell you all about it.
Yes. So how do we combine all of this into a final binary? And we've still got to consider here that we still want the automatic type registration in QML modules to work in the CMake case. So to build this all together, we have multiple things that we need to combine. We've got the Rust code itself, any macro expansion, any generated C++ code, anything from mock that was generated, any initialization for the types or Qt resources, and any existing QML or widgets code. But we have a problem. Rust uses Cargo, and Qt tends to use CMake. So in CXX-Qt, we have to support both. So let's first look at a Cargo build and how this works. It starts at a build script. What a build script is in Rust is it allows you to write Rust code that can run before the Rust compiler. And this allows you to specify tasks you need to do before the Rust compiler runs. And you could then create extra information, or you could pass things to the linker. For the build script here, we use CXX-Qt build. This is a library we've written to help you run the build script, and you tell it which files to look in that have the macro. Once it finds the macro, it then does any code generation that it needs to for the C++ side and automatically runs mock for you. You can then tell it to combine existing QML widgets code, and then the Rust compiler will do the macro expansion as usual. And finally, at the end, Qt combines everything. The cargo combines everything into a final binary and links it to Qt. And you're able to tell CXX-Qt build which Qt modules you need to link to, and even where Qt's coming from or which Qt version you want to use. So that works for cargo builds, which are kind of simpler in the end. CMake is a little bit trickier. So let's look at CMake. So we have CXX-Qt CMake module, and this is a helper module you use. And you tell it which Rust crate you want to import. So you point it at your Rust crate, and this uses another project called Corrosion. And Corrosion, you point it at a cargo file, and it can automatically run cargo for you and then give you CMake targets that you can then link to. So it nicely integrates cargo into CMake for you. And this is even useful outside of CXX-Qt for just normal integration of Rust into C++. So this then calls our build script. The build script runs like previously, but with some subtle differences here. It instructs cargo also to export our C++ headers and export the initializers which we need for the QML type registration, or the resources, etc. And instead of building a final static library, we actually, instead of building an application binary, we end up with a Rust static library. And then this is combined together with your existing QML and widgets code, and everything is linked in CMake together as usual. So this allows you to easily take part of your application and link a Rust module for just part of your backend. So Leon, what does this mean for integrating Rust into Qt applications?
So if we go back to our overview slide again, we again had these three big building blocks that we needed to address. And with CXX-Qt, I would say this is pretty much where we're at right now. We, for Qt API bindings, have most of the very fundamental types, QString, QRect, QVector, you name it, like the types you usually have in signatures and return values. Those are all there, and they're all of very high quality, and they're very easy to use from Rust. So that support's great. What we don't really have ourselves set as target with CXX-Qt per se is to wrap all of the Qt API. That's just a huge API surface. And the point is, CXX is already really good at this. And it is so easy to basically import types from Qt that we'll just leave this up to community support, and we already have a crate for it where anyone can like throw in a binding here or there for this type or that type, and that works pretty well. And you've even seen, like, for example, QAbstract list model, we just imported from C++, and we did not need CXX-Qt for this. This was all just CXX, and it took us 2 lines of code. So lots of that we can just leave up to CXX and the support for integration there. Then when it comes to mock for Rust, QObjects are supported. We've seen them. You can do QAbstract list models, all the good stuff that you need. You can create your own signals. You can also connect to slots. Closure, which you can currently only do so with closures. Direct connections are sort of work in progress because they're a bit hard with all the templating that's involved there, but we're working on it. Then properties are also fully supported. We've even kind of done our best to make the boilerplate there a little bit less, like you don't have to write the 100 getter for a member. So that part's pretty nice, I would say. And we can, of course, export these types to QML. And we can do a lot there with, for example, type registration, which we've also solved with our CMake integration by sort of recreating a lot of this in Cargo and basically integrating it into the Rust build system. And we can, as you've seen, do QML modules, QRC, all of that stuff from Rust. And one fun fact is actually, by that support, you can actually do QML modules with CMake, with Qt 5, or at least 5.15, as long as you're using CXX-Qt, which you actually can't in normal Qt. So that's kind of a fun fact, I would say. And yeah, that's kind of where we're at right now. One side note, we haven't yet bothered with QGadgets because we haven't needed them yet, but there's no fundamental reason why we can't support them. So someone ever needs that, let us know. And of course, all of this is free and open source, so you can find us on GitHub and just try everything. It's MIT or Apache 2 license, so very liberal licensing without a copyleft. And feedback and suggestions are, of course, always welcome. Open some issues, join our Zulip, whatever you like. And you can also visit us at our booth, where we also have a small demo set up of how an application like that can run, for example, even on a Raspberry. And now is a good time for questions.